We mainly discussed on two. Last week we have a deficit
有没有那烧烤味？
and also a breakfast.
还好，没有
我。一直迷茫。
So if you remember, deficit is when the agents will explore the node
我有吸，我非常。
branch by branch, level to level, level to level first, until there is no solutions. Then only you will consider the node that's placed beside the D here, same levels, right? So it will expand, right? Then continue the next level. If no, then backtrack, expand again, right? So this is level
第一次。
followed by side to
好
side
像
here.
是头样子。
But we know breakfasts is the another way round, so the agents will perform the search side by side first. B, C, D. Right, so you will actually check, is it B, go? No,
我知道
check,
这题。
check, okay, no solutions. There's no solutions under the A, so you will go to the next level, expand the B,
明白。打击。
right, check, is it the go? No solutions, go to the next, go to the
影响。
next. Right, so you can see here is actually side to side here.
我治好。
And then only followed by level, right? So that is another two approaches. Deficit level by level first. No solution, go to side. Go to the side.
精神。
Breakfasts go to the side first. Right? If no solution, go to the next level. That's it. Okay, and last week as well, we do cover from the machine perspective, how the machine actually explore the node. If the deficit, then we will normally check the closed list. Yeah, we will check the closed list. If there is a repeated node or not. For breakfasts, we check both open and the closed list.
Impact
Right,
是
we
我
check
可以
to
影响别
avoid
人。
repeated state. Okay, to check whether the agent already at the go state, we check the close state as well. Yeah, we check the close state as well. To check if this is the go state. Okay, for the preferences, same, we can either check the open list or the closed list. Right, so open, then we use early go test, close, we use late go test. That's it. Yeah, so this is from the machine perspective, we need to treat array, you will still remember, so that the machines will know which node to store. And then which node that it already expanded and which node that it don't want to expand due to the repeated state. Okay? Right, so that's it. And one thing you have to remember that in the dry search, the agents will not utilize any value, any cost, any distance to perform the search. This is one thing that you have to know. And in this chapter 4, informed search, I want to show you how the agents perform the search with the help of the cost, with the help of the value. Right, so agents will perform the search based on the
很多
value.
东西都是会 last
Okay.
minute 的，然后没有 plan 的。
Okay, good. Right, maintain this. Maintain this. Alright, so
可能是因为你
done. So this one is last week. If you cannot remember, so this is just a revision for the uninformed search. So in chapter 4, we have informed search, but it's inform and information. So information, so means that agents will use the information given by someone, maybe us or maybe by some functions to generate calls. Right, so let me give you some ideas of what's meant by the heuristic search first. Okay, so assuming that you have the state, right, so this one I clean, huh?
Orange，
还是很多人说 orange。
不是 Orange，
有别的朋友是别的颜色。
Okay, so what's meant by heuristic search? So imagine that you are in this stage.
green 是
Green 它
A
会比较，
stubborn。
它不是 stubborn，
Okay, this is a very big space here, big problem space or state space here.
它会好像
Okay, so at this stage, we have state A. Let's say now you are
好
here.
像你自己讲你要
So we are going to use some functions or use some calculations to generate the cost here.
大概这样子，
For example, the cost that we obtain at this stage is, let's say, 10.
感性，它会
Okay, let's say the cost that we obtain. Don't worry about how we generate the cost. Later we'll go through a lot of functions and examples how to generate the cost here. At the same time, we have to find the cost using the
勾是
same
不要
function as
planning，
well
哦，它是 go 诶，
for the goal state. Let's say the cost that we obtain is let's say 20.
你叫他做一个东西，他会一直问你问题。
So why the main how the agents will utilize this value? The agents will actually compare. Oh, 10. Now the goal state is 20. So it means that we are still far from the
那种
goal.
有用问题
We just compare the value.
有用
Right,
问题
20, 10. So I'm 10, but the goal state is 20. So I'm still far from the goal. So what we do here
其
is
实还没有
we can extend
他是要先
the possible nodes
叫
here,
这些，等一下要想一下先。
right, and use the same function to generate the
好
cost.
像也是 go 诶，
For example, the cost here is let's say 14. So let's say this is
没
8.
有，没有随便讲，
Let's say this is 16.
全部平等。
Okay, so again, the agents will compare this value with the goal state. Right, so which one do you think is very close to the goal state?
他是差
B, C or D?
我的差
C.
20多不是。
C.
那个
C
A
closer to
是
the
的
goal state.
A 是的那个叫什么 CEO，
A
是 blue 诶，
8 compared to 20 closer or 14 compared to 20 closer or 16 compared to 20 closer.
它会
Huh?
T 会
D, right? So is it 8 minus, when 20 minus 8, you still have 12, right? So 20 minus 16, you have only 4. So meaning that the agents will know, okay, D is very close to the goal state.
这样我就不能
That's why the agents will continue expand from here. Let's say you have E, you have R here. Again, we generate cost, let's say you have 18, let's say you have 19 here. Alright, so again, the agent perhaps may consider again, right? Let's say we expand this. Alright, so compare again, which one do you think is closer to the goal state? Again, based on this, which one is very close to the goal state? Based on that value. F, right? So now, it means that the agents will perform the search based on this information, kind of a hint, right? So agents will continue, okay, so let's say now you have HN 20. Oh, so now, so we already arrived at the destination. So what is the difference between this and the blind search? You still remember the blind search, let's say breakfast search,
都会重复的。
right? So breakfast search, whether you like it or not, the agents will expand all the possible.
我也是忘记我
Right? It's no solution, you will expand this, let's say. Right, expand
那一
this.
次只可以剩100个，然后100多个。
expand again. So you will actually somehow explore unnecessary path here. So we know that the goal state is around here, but due to the pattern search for the preferences, you will actually expand all, right? Because there's no information provided to the agent. So this one, you see, we don't need to waste time to explore this area. So by using the so-called heuristic search, the agents is able to perform the search more efficient. Lesser time, lesser memory. Alright? Is that clear? Right, so that is the general idea. So we have several algorithms here. For example, hue priming, basket search, instant search. The idea is about the same. The idea is about the same. We based on the values, we want to use some things to generate the value, and the values used to compare with the goal state. And see which one is very close to the goal state, then the agents will go for it. That's it. So we no need to waste our time to explore unnecessary stations
要
here.
录完了。
Okay? So what is this value means? So these values mean for heuristic cost. Okay, so this HN here is all referred to heuristic cost. So how to generate the heuristic cost? We need heuristic functions. Right? So heuristic function is the one that used to generate the cost. How to design the heuristic functions? It depends on your experience, depends on trial and error, depends on experiment. So when you design the heuristic function, you need to do some research, like what kind of the game is it, and then what kind of the function is suitable for the games. But fortunately, for your level, you are not required to design the functions. You're just required to find the cost from the given heuristic function. Meaning that in your midterm in your exam, you just need to know how to find the cost from here. So this one normally will be given. Unless you want to do research, unless you want to further study your master, your PhD, perhaps you need to design your own heuristic function. Or sometimes even you do you study master or PhD, you are not required as well to design the functions. Yeah, sometimes we just use whatever people has been designed. You just study the journal paper and then you just use other people's functions. Okay, so that is the general idea. You have to understand what's meant by the cost. Why we need a cost? The cost is used to compare the current state with the goal state so that which one is closer to the goal state. Okay, then the function is the one that we designed to generate the cost, right? So this is one of the examples here. So this is one of the examples. So the function that we generate here is the numbers of tiles at the correct position. Right place means correct position, not right position. It means that the number of tiles at the correct position. So how to find the values here? You can see that we have a value 4 and value 8 here. Okay, it is very simple. Okay, so the function, let's say we design, right? Let's say we design is very simple. We just need to calculate the number of tiles at the correct positions, right? In order to know whether it is at the correct positions, we just need to compare a reference. So this is the reference, right? So this is the reference, and this is the correct. The tiles that at the correct position means it's 1, 2, 3, 8, 4, 7, 8, 5. So this is the goal state. Right, so we just need to compare the initial state. Let's say the current state is Q83, 164, 75. Right, so let's say this is initial state. Right, and this is the goal state. Okay, so how to compare? We just compare the position. We check this position. Then this position is value 2. But this position is value 1. Is it correct? Correct position? Wrong position. So we don't give any points to this tiles here. Then we go to the next one. In the current, this current state here is 8. But this position is 2. Wrong again. Check the third position. Having value 3? Yes, having value 3. So this is correct. So we add a positive 1. Compare these positions with these positions. This is value 1, this is value 8, wrong. Position 6, okay, so this one no value. We don't compare the empty tiles usually, right? 4, okay, 4, yes, correct. So we'll add positive 1 here. 7, yes, 7, yes, correct. So empty tiles we don't compare. 5, yes, correct with positive 1. So that's why you add up together 1, 2, 3, 4, you will get value 4 here. That's why this is how you get the value h equal to 4. Right, so by using the functions, calculate the number of the correct positions here, you'll get Hm equal to 4. That's it, as simple as that. Right, the function that we design is pretty straightforward for this case. Right, so this one is very simple because the problem is not involved a big problem space here. So that's why the functions can be solved easily. So now we compare the goal state. 1. The goal state also 1, so positive 1. 2, okay, positive 1. 3, also 3, 8, correct, okay, 4, correct, 7, correct, 8, also correct, 5, also correct. So add up together, so you will get 1, 2, 3, 4, 5, 6, 7, 8. You will get 8 here. That's it, done. So meaning that you have 4 at the current state and you have a heuristic cost 8 at the goal state. We just compare to the reference to the goal state. Then you know how many are actually at the correct positions. That's it. As simple as that. Okay, yeah? No problem. Okay? Good. Okay. Alright, so we have actually 4 algorithms in chapter 4. Yeah. Hill climbing here, we have 2 so-called algorithm. It's known as the simple hill, steepest ascent hill climb. And then we will move on to the fastest, and lastly we will move to the A-star. Just for information, hill climbing is not a very good algorithm here. It will not guarantee the completeness. Meaning that you will get stuck at somewhere and you will not return the solution to you. You will know why later on. Okay, so let's start with the hill climb. Okay, hill climb is the simplest way in a heuristic search, but however there are a lot of limitations. Less combinatorially but explosive as it serves locally rather than globally, possibly very inefficient. Yeah, so this is very not efficient because or you know why later on. I will show you the algorithms later. Okay, so we have two algorithms under the hue priming. Okay, the first one is known as the simple hue and steepest ascent hue prime. So I'm going to draw here so that you can see the comparison. Okay, so this is simple hue prime. Okay, simple hue prime is something like a deficit, you know. Something like deficit. If you still remember how deficits work, you will explore the current fringe, right? Explore the current fringe. But if you look at our algorithm here, select an operator. Operator means that movement, left, right, up, down, movement operators. Apply to click a new state, evaluate the new state. Okay, the third one is very important. If new state is better than the current state, perform movement, making a new state. So this is very important, remember this. If the new state is better than current state, it means that if the new state, this value, is better than the current state, then the agents will continue the expansion. This is the limitation for the hue prime. If this state, let's say look like this is worse than the current state, the agents will just stop here. Yeah, that is the idea. This is the meaning of the third point here. The new state, the better than means that the heuristic cost must better, equal to cannot, must better than the current state, the agents will continue to move. Why? Because this is hue prime. You are priming the hue. So this is the goal state. You're definitely looking for a so-called a path that is deeper than the current state. Right? Correct or not? You're priming the hue, that's why you are moving upwards. That's why you will say the new state must better than the current state, then only we will continue, then only we will arrive to destination. Definitely you will not, you will like moving down already. Definitely the goal is not here. Right? So meaning that you are here, if the value is worse than the current state, definitely you are moving downwards. You are not going to the goal direction. That's the meaning. That's the meaning. Right? So we look at how it actually works. Okay, same state, we use the same state here. For goal state, we having 8 here. So using the function number of tiles at the correct positions. Right, let's start. Okay. So you see here. Right. So your current state is at 4. Your goal state is at 8. Meaning that now you want to move to the bigger value. Your direction here is to move to the bigger value. Right? Your goal is 8 is bigger than 4. That means we have the idea that we are going to moving to the so-called the higher values here. And you have 4 operators. You're going to move the empty tiles according to up, right, left, and down. Right, so this one we have learned last week, successor functions here. Okay, so we'll start here is, okay, 4, there's no way, it's still far from the goal state. So it looks like a deficit. You will just expand in one direction. Although we can move 3 directions here, we can move left, we can move right, we can move up, but we will generate only the first successor using the first operator up. We move up first. Right, so it's like a deficit, one direction. Okay, so you move the up directions here. We calculate the cost. Right? How many correct tiles? 1, 2, 3, 4, 5. 5 correct tiles. That's why you have a value 5 here. Okay? Can Alright, so you have value 5. Now the question is, does this value better than 4? Yes, it fulfills the requirements for a simple hue prime. This must better than this value. Right, so how to know when it's better? Because it's closer to the goal state. That's why we know that this is better than the current state here. Okay, expand. So what is the next operator? You go to the next level, you move up again. So this empty tile, you slide up. The moment you slide up here, you calculate again. 3, 4, 7, 6, 5 are the correct positions. So you have again H5. So does this value better or equal to the current state? To the parent state? Equal. Does it better? No, right? 5 here, there's no better, so it's equal.
So what we do here is like a tag process. So it means that this is actually dead end. So it will go backtracking and search another successor here. Right, so the next successor is moving right hand side. Moving right hand side. So you have how many correct counts? 1, 2, 3, 4. 4 better than 5. Is it? 4 better than 5? Worse than 5. So again, so this is not a good successor, die already here. But move to the next successor. Right, so you move to the left hand side. Right, the third operator move to the left hand side. 1, 2, 3, 4, 5. Again, so you have 5 values here. Right, you have a value 5 here. So is it better? No, it's equal. So do we have any other movement? No more, right? You cannot move down. Right, if you move down, it's actually go back to the original state. So start here, that's it. The hill climb will not do backtracking furthermore, you will just get stuck here. So you will actually remove this from the memory. Once it explodes, you will actually remove from the memory in terms of the coding. Right, so it will not store the record, so it will get stuck here. Right, so there's no better value. As long as there's no better value compared to the parent state, then you just stop there. Okay? That's it. So this is the algorithm for the simple hill climb. And it explodes according to like the depth search patterns. Only one direction. Okay? Okay, another example here. Okay, so same functions, number of tiles at the correct positions. So at this moment we have 1, 2, 3, 4, 5, 6. 6 value here, value 6 here. 6 is quite pretty close to the 8 already, right? We know that we are almost there. Alright, so let's move on to the successor. Move up, we can't move up here. Move left, yeah, so we can move left. So we move left, alright, so better, right? We have a 7 correct value here, we're very close to this. And the most importantly is this value must better than the current state. Then only we will continue. Right, this is better, right? Let's continue. Go to the next level, let's move up. If you cannot move up, move left, cannot. Move right, cannot. Back to our original state, we have only one operator here, down. We move this empty house down here. Right, the moment that we move down, then we get the value 6. Right, so any other operator that the labeling, no more. Right, so again, we start here. Right, so because this value is worse than the current state. Right, so we stop here. So here, from here, these examples, what we know here is you have to always remember the expand one direction, right? And we always check this value. Let's say H5, this is H6. Okay, so this is better. Yeah, but before that, you have to check what is the value for the goal. Let's say your goal is value 8, then it means that we're having moving towards a bigger value here. So 6 is better than 5. So let's say now you have H equal to 6. Okay, so 6 is equal to 6. So it will not continue. So this one consider that end. So it will try to explore another nodes here. And 5. Let's say H equal to 5. Okay, 5 worse than that. Okay, so this one also that end. Okay, let's say no more successor, then the algorithm will just stop. You just stop here. That's it. So the agents start at these locations. Okay? Alright. So what is the there are some terms to describe these phenomena here. Let's say now you have value 5. Right, so let's say imagine that you have a value 5. Okay, so you go to the value 6 here. You go to the value 6. Right, you climb upwards. Right, so that essentially this is the goal. Okay, so pretty good, right? So let's say assume that the next state drop to value 5. Drop to value 5 here. Okay, so this phenomenon is known as foothill. It's just a term to describe it. It means that you move upwards, suddenly you drop back. So this one is just a foothill, right? So sometimes you may have this phenomenon, right? So you have value 5. You move next station, 6. You move next station, also 6. You move another direction, also 6. So you see that all successors here are all value 6. So there's no pattern, right? So there's no pattern, right? So this phenomenon is not as plateau. Means that the agents move crime until there is a kind of a flat, so-called a flat path. All the paths are actually flat, so he confused, don't know which to go. So this phenomenon is just known as plateau. It's just a name, just a name. Okay, so far so good. Don't worry about if you don't understand what is meant by foot heel, crack heel. Don't answer, it's okay. But as long as you understand how the simple heel climb works, right? It's just like the deck process. Move one direction and check is it the current state better than the current. If yes, continue moving. If no, go to successor, another successor. Right? If no, go to another successor until there's no more successor, then the agent will just stop it. Okay. Okay, so let's move on to the next algorithm. Is known as steepest ascent hill climbing. Okay, steepest ascent hill climbing, it behaves like the breakfast. Okay, steepest ascent hill climb behave like breakfast. Okay, so this one, simple hill climb, it explore one direction, right? We don't care what's happening here. Steepest ascent hill climb, imagine that you have H5, so it will explore all successors first. Right, so let's say now this one is H3, H6, H7. Alright, so the successor, the agents will actually compare. Compare which state having better value than the current state. And among the all, they are the highest value. So which one is the best? 3, 6 or 7? Definitely 7, right? So 7 is the best, right? But you have to fulfill the requirement that must better than the current state. So among 6 and 7, 7 is the best among the all. So it will just explore all. Alright, so let's say now you have 8, you have 6, you have 4. Again, compare again, which one is the best, but at the same time must better than the parent node. Definitely this one, explore again. Check whether is it goal. Let's say the goal is 8, so define the solution. So it will expand all and search. So this steepest ascent is able to solve the problem for the simple hill climb where the agents will ignore this part. The agents will ignore this part, and this part will not store inside the memory. So that is the problem for the hill climbing. So this is nature for the hill climbing algorithms. Right? So you will say whether it's a good algorithm, no, because it may get stuck at a certain level, and it does not allow to do backtracking. In terms of the so-called algorithms, the nodes will be actually removed from the memory. Right? It will just always store the latest node with the horse. That's it. Is that clear? Okay, so let's move on these examples here. Okay, so same, we have 2 correct tiles, so okay, same function, number of tiles at the correct positions. So we compare the current state with the goal state. We have only 2 correct tiles, so H2. They are still far from the goal state. We explore all. Why we explore? You look at the simple hill climb, we explore only one successor. Steepest action, we explore all possible successors. Right, moving according to the up, left, right, down. So we move up, left, right, down. So we have a 3 successor. Down we cannot move, that's why it's not valid. So we have a 3 successor and we compare this value. 3, 1, 2. Which one fulfill 2 criteria? Which one is the best? And which one is better than the current state? This or this? This, right? Value 3. So we will continue explore from the first successor. Explore. Alright, so we can move again up, left, right, down. We can move up, left, right. Down cannot because it's a repeated state. So again, compare. So down, all this value better than current state. 3, 3, 3. Current state also 3. So cannot. So get stuck. The agent will just stop and then. So what's the problem? What's the name for this phenomenon? What's the problem for this phenomenon? We have 3, but in front of the successor, all same value. RDB already. Plateau, right? Plateau is where you go 3, then all the direction also 3, 3, 3, flat, kind of flat here. So this phenomenon is known as plateau. Yeah. So again, the agent gets stuck at this position. So simple hill, simple ascent hill climb, guarantee completeness or not? No. Right? Depth first, breadth first, yes. Depth first, breadth first, we search level by level until we find a solution. Although it may take a lot of time and a lot of memory. But steeper or steepest hill climb, there's a limitation where it does not allow to do backtracking, not allowed to revisit the previous node. That's why you will get stuck whenever it found, whenever the successor is not better than the current state, then you will get stuck at the next levels. Okay? Alright, so one more problem with the steepest ascent hill climb. One more problem. What is the problem here? Assuming that, now you have a current state having a value 2 here. We expand all right, so you have 4, 2, 3. You have 4, 2, 3. But what steepest ascent hill climb say? We choose the best one. Right? So the agents will choose the best one, which is 4. And this 2, 1 will be removed from the memory already. Will be removed from the memory. So it will continue to explore this path until it finds a solution. What happens if let's say this is the only path, this is the path that actually return you the optimal. Let's say after this stage, it arrives to goal. So that is one of the problems. But the steepest ascent hill climb will remove these 2 from the memory. Although this path possible, right, give you the optimal solution. But however, due to the nature of the steepest hill climb, it will only consider the node that's the best, which is this one. And then maybe this one will take longer path to arrive at the solution, but maybe another path here is actually the next step you arrive at the destination. So this problem here is known as a bridge, RIDGE. So where you go and ignore the path that may return you optimal solution, and you go another path that may lead you to the field or maybe not optimal due to your selecting the best one. Yeah? At this level, maybe this is not the best, but this could be the path that return you optimal solutions. And this problem is known as bridge, RIDGE. So you can just look at the next slide here. Right, so we have a 3 problems. I mentioned foothill. Right, foothill is where you are going up, suddenly you drop down. Right, plateau is where all flat. Right, ridge here is where you take longer path, where there's another path that can return your solutions, optimal solution, but you take longer path because you're choosing the best value among the all in the steepest ascent hill climb. So these are the 3 problems that you may find in the hill climbing. Okay? Is that clear? So far, so good. Okay.
Take 5 minutes break.
Okay, so to design the heuristic functions, we have 2 types. Usually, we can design according to local heuristic or using a global heuristic. So this one is out of topic. So this one out of topic, right? So we have algorithms. Let me show you.
所以如果你用那个 web 的，它直接给你导入了，你用这个 app 的。
Okay, so we have, remember we have line search,
你可以不要呀。
we have the heuristic search.
一个一个按哦。
And heuristic, we have mainly 3 algorithms. Hill climb,
应该不是我的问题
we
吧？
have a best first,
它的网速问题。
we have A star. Right, under the hill climb, we have another 2 algorithms here. Steeper hill climb, we have steepest ascent hill climb. Okay, so all of these algorithm, okay, is actually depending on the heuristic
我先玩了。
cost,
是的。
right? Right, so this algorithm is actually depending on the heuristic
已经
cost.
1.7个 GB 了。
And how to get the heuristic cost? You need
我有10个 G
to
哦。
design the heuristic
整出来1个 GB 不到应该。
functions
整出来1个 GB 不到。我闻一下。
to generate the cost,
That's right.
to apply the cost into these 4 algorithms
飞可以
here.
太走啊。
Okay? And then this is a little bit out of topic, so this slide onward is just to teach you how to design the heuristic functions. Right, so we can use local heuristic functions or we can have a global heuristic function. Yeah. So meaning that if local, we just consider the small array. Right, global means that we consider a bigger picture and design the cost. But either local or heuristic, it does not guarantee you find a solution. Maybe it may fail the
solution as well. Because we are the one who design the function. If you don't have any experience, then the function that we design definitely is not really good. So we have to do a lot of research. So this slide is not, just for information, additional information here. So let's say in these examples, let's say we design the local heuristic functions.
你是要讲的是
We design that, okay, if the block rests on the correct position, we give positive 1.
你是要
If the block placed on the wrong position,
你想出
we
出的那个
minus 1. That's it, a simple
是要
function
给
here.
它消还是
Right, if the block placed on the correct position, positive 1. Wrong position, negative 1. So how to know that it's wrong or right? Just compare with the goal state. Always take the goal state as a reference to compare. For example, in this case, C.
有一些片段
C placed as A. Please place on A block here. But at the goal state, C, suppose placed on table, let's say. So wrong or right? Wrong, right? C placed on the A. But supposedly C placed on the table. So this is wrong. So negative 1 here. A placed on B. A compared to the goal state. A, yes, A suppose placed on the B, so it's correct. So we assign positive 1 to this block. B placed on the table. But at the goal state, B placed on the C, so it's wrong. So we assign negative 1. So add up negative 1 plus 1, negative 1, you will get a cost negative 1. That's it. As simple as that. Yeah, we just focus at the local position. We don't care about what's happening in B, what's happening in the upwards. We just focus at this position. Okay? So, if we use Taper's SNQ prime here, so let's say we have a CAB, negative 1. So we can put only C on the table. There's no other movement. You can place C on the table. Yes, there's only movement here. So after you place, you again generate the cost here. A placed on the B, correct, so positive 1. C placed on the table, yes, correct, positive 1. B placed on the table, wrong, because suppose you should place B on the C here. So positive 1, negative 1, so you get positive 1 here. Positive 1 better than negative 1, yes, we can expand. So expand, you will get negative 1 equal, see, we get stuck here. So negative 1 is worse than positive 1, negative 1 also worse than positive 1, so we get stuck. So what we can say here is using a local heuristic, you are not able to find a solution using the Taper's SNQ prime. So perhaps you can improve using global heuristic. We look at the bigger picture. The design, the course here. Alright, so okay, look at the formula, heuristic functions. For each block that have the correct support structure, the support structure means that you have the correct blocks to support it.
要做吗？
Okay, so it means that, okay, so let's say this is the goal state. So you have A, you have B, you have C. Let's say we look at the block A. So what's represented by the support structure? The support structure means you should have this B and C that are used to support the A. So this is whole support structure.
你很卷哎你，
We have two blocks that used to support the A. So this is called
上
support.
课不要好好上课啊。
For each block that has correct support structure, add a positive one
freelancer.
for every block in the support structure. Alright, so let's look at this A. A is supported by these two blocks here. So 1, 2.
赚大
So
钱
we
记得不要忘
assign
记我哎。
positive 2 to block A. So that's the meaning. Okay, so that's the meaning. So correct support structure. So if you look at the current state CAB. Okay, we compare with this goal state. C support by A and B. But C support by nothing. There's no block used to support a C. So C is wrong. It's wrong, we assign negative. So what is the value here? The value is depending on how many blocks that used to support a C. 1, 2. So we put negative 2. Now we look at block A. Okay? Block A supported by this support structure, which is B. But look at this A. A is support by this B and C. You must support by this support structure B and C. But this is wrong as well because you only support by B, negative. How many blocks? 1 block, so negative 1. So B, there's no support structure, so we assign 0 here. So add up together, you have negative 3. Fantastic. That's why you have a negative 3 at the initial state. Yeah, you have a negative 3 at the initial state. Then you explode, right? We expand. So expand. So you can see that using a simple hill climb, eventually it will tell you the solution, right? It's able to you stack. This kind of means that you stack the block. You put a C on the floor first. Then you have two options. You can put A on the floor, or maybe you can put A on the C. You have two options here. Right, so in this case, you can put B on the C, or you can either put B on the A here, then you stack, eventually you find the solutions. So you can see that by using the global heuristic function, it is able to return you the solutions, either using the steepest action or simple hill climb. Both return you solution. Okay, so just to let you know that we have a different way to design the functions. Either you just look at the smaller picture or you look at the bigger picture. But both do not guarantee you the solutions or optimal solutions. Yeah, but from this exercise or from these examples here, global heuristic returns you a good so-called solution compared to the local heuristic. But anyhow, you are not required to mention. You are not required to design unless you are interested. Then you can just explore more from this slide. Otherwise, then it's okay. Yeah. Okay, so we will stop here at for 10 minutes, right? Then we will continue with remaining two algorithms here, which is very important: best first search and A star search. Okay.